Okay, so it's a pleasure to be here. And so I tried to cut down the topic a little bit from foundations to the symmetries of general relativity. And I'm going to go into, I'll start with the beginning, some discussion of the symmetries, and it will evolve into a kind of story of a triangle involving three different ideas that have come up in general relativity over the last century. So what are the symmetries of general relativity? So this is a subtle and often ill-posed question, and it's actually been the source of consternation and confusion for almost all of the last 100 years, certainly still is now. And our answer to that question has been changing over the years. And right up to the very present, it's been changing. So a common answer that is given to this question is that the basic symmetry of general relativity is general covariance. It's a symmetry under the relabeling of space-time coordinates. Now, the IAS is mostly a theoretical institution, but every once in a while they do an experiment. And in the year 2000, there was an experiment done in which they relabeled the coordinates. And what had once been Einstein Drive moved from the north to the south of Olden Lane. And Olden Lane was mapped to a double cover of itself, and Earl Lane appeared. Now, fortunately, the mathematician at that time the director at that time was a mathematician. And he was able to do the coordinate transformation in directing the new members from their offices to their homes. And it was found that the members actually arrived from their offices to their homes in exactly the same amount of time, thereby verifying general coordinate invariance. Now, it was not an invertible transformation, but I don't know. So, okay. But the fact that general coordinate invariance is not the same thing as the equivalence principle that was a continuous factor in Einstein's development over those many years of the general theory of relativity. And there's an amazing quote from a letter to Ehrenfest in 1913 that he says, one can specifically prove that generally covariant equations which completely determine the gravitational field from the matter tensor cannot exist at all. So Einstein ate his words a year and a half later, but even right up at the last minute, it was not obvious in what sense this relabeling of space-time points was a basic symmetry of general relativity. So nowadays, we talk about redundancies of descriptions. And general covariance, in large part, might be viewed not as a fundamental principle, but as a redundancy of description. And a similar concept has come up in gauge theories, where in non-abelian gauge theories, work of Seiberg and others on duality has emphasized the point that gauge symmetries are not necessarily fundamental, but they're redundancies of description, which we should distinguish from physical symmetries. Physical symmetries tell us about measurements, relate different physical processes, they lead to conserved quantities, and so on. And indeed, since this is conference in part pointing out the important things that happen in general relativity right here in Princeton, in 1960, Tullio Reggie gave a much less redundant description of general relativity, just in terms of gluing together simplicial triangles known as Reggie calculus, that did not have general covariance in the same sense as a basic symmetry. But we don't want to throw it out altogether. So in special relativity, we have Poincare invariance, And these Poincare symmetries lead, via Nether's theorem, to measurably conserved charges such as energy, momentum, and angular momentum. And indeed, we heard in the historical lecture this morning about how Einstein was very important to him that energy momentum conservation would come out in a good way from his general theory. And indeed, but energy conservation is energy is the conserved quantity associated from symmetry under time translations. T goes to t plus a constant. But since t is a time coordinate, this is a coordinate transformation. So obviously, we don't want to say that all coordinate transformations are related to redundancies of descriptions. Also, boosts, for example, if you boost an object, that can be thought of as a coordinate transformation, but it changes its energy. So it's not just a redundancy of the description. So in the 60s, Bondi, Metzner, and Sachs asked the question, how do we get this structure, which is so important to everything we described before, out of general relativity? In what sense do we get the Poincare symmetries and charges in general relativity? Sounds like a simple question. I think they were imagining it would be a simple exercise and they would reproduce it. But the answer was a huge surprise. The answer is you can't. And how did they set this problem up? Well, first they introduced the notion, actually Arnowit, Deser, and Misner had really pioneered that 10 years earlier, of an asymptotically flat space-time. So here's a picture of a space-time, and it's a space-time describing an isolated system, which at large distances is flat, but might have a strong gravitational field or anything in a black hole. A black hole or anything could be in the middle. And here's a picture of such a space-time, which we'll use again. It has important regions. This is the interior of the space-time. It has a place where light rays go to, called future null infinity. And it has a place that light rays come from, called past null infinity. And I've pulled infinity into a finite region to draw this picture. But I've demanded that light rays, I've drawn my picture in such a way so that light rays go at 45 degrees. So this is the origin of space-time. And out here, the radius of the two spheres is going to infinity at both past and future null infinity. This is called a Penrose diagram of Minkowski space. And an asymptotically flat space-time is one that approaches Minkowski space in some suitable sense in this region, but complicated stuff can be going on in here. Now, being like Minkowski space near Scri plus is a very technical, subtle, mathematical problem to specify exactly what that means. And indeed, a subject on which there are mistakes, many, many mistakes in the literature. I think it was cleared up, largely cleared up only 20 years ago by the work of Christodoulou and Kleinerman. And we'll come back to that. All right, so now you have such a space-time, and you want to ask, what are the symmetries of a space-time? So then the notion of asymptotic symmetries was introduced by them and greatly refined later by Reggie and Teitelboim. And those symmetries are coordinate transformations which preserve this boundary. In other words, they're smooth and they map this boundary into itself. And you divide it by the trivial coordinate transformations, which you need to define carefully. But roughly speaking, they're the ones that just correspond to redundancy of descriptions. Another way of saying it is that there are coordinate transformations that don't affect any of the physical data that specify the system at past or future null infinity. So you might have thought that this quotient, so there are infinitely many coordinate transformations, infinitely many trivial coordinate transformation, and what was hoped was that this quotient would be the Poincare group. That's what they were expecting to get. In fact, it's not what they got. They still had infinitely many, this was in 1962, more than half a century ago. They still had an infinite dimensional symmetry group, which is now known as the BMS. I've put this plus on here because I want to distinguish between the symmetry group that acts on future null infinity and the one that acts on past null infinity. And this group consists of a semidirect product of the ordinary Lorentz transformations, and then the so-called supertranslations, of which there are infinitely many. Now, we might have expected a symmetry under which retarded time, so by retarded time I mean t minus r, is shifted by a constant. That would just be the ordinary Hamiltonian. But in fact, you can shift it by an arbitrary function of theta and phi. And these symmetries cannot be thought of as redundant descriptions of anything because they clearly act non-trivially on the outgoing physical data. So for example, here we could take a spacetime in which there are two gravity wave pulses coming out at the same time, one at the North Pole and one at the South Pole. The supertranslations will map that because we're allowed to translate forward in time the sphere at null infinity at an arbitrary rate at different points. We'll map that to a situation in which they come out at different times. So it's surprising. It's not intuitively obvious. It was a huge surprise to these people. They wrestled with it for several decades. They reanalyzed it from many different points of view, and they kept coming to the same conclusion that these were non-trivial symmetries that act at future null infinity in general relativity. And there was no meaningful way to reduce this to the Poincare group, despite many attempts at doing so. So what do we do with this symmetry of GR? You would think this is the world is described by general relativity. The asymptotically flat approximation is good for many things, or even most things that we want to describe. You would think that every textbook would begin with a discussion of this symmetry principle the way special relativity books begin with the Lorentz group. But we don't really know, but I would guess that the vast majority in this room have not even heard of this symmetry group. And what happened was this. The problem was that you need to join the action of this symmetry on future null infinity to that on the past to get a symmetry of gravitational scattering. And for example, we can't, if we have some solution of general relativity, we can't do a Lorentz transformation on the incoming configuration and not do a Lorentz transformation on the outgoing configuration. The symmetry of scattering has to involve a BMS transformation both in the future and in the past. You wouldn't do time translation in the future and time translation in the past. That couldn't be a symmetry of scattering. And so you want to join these two groups, but there was a lot of confusion about the nature of this point, spatial infinity. So future null infinity and past null infinity meet at spatial infinity, and there was a lot of discussion in the mathematical physics, the relativity literature, mathematics literature about the structure of this point. And most of it was wrong. And they concluded that there is no way to tie together the symmetry group in the past and the symmetry group in the future, and there's no way to have a symmetry of gravitational scattering. The symmetry that BMS acted on was just a symmetry transformation on the data in the future, a symmetry on the data in the past, but not a symmetry of the scattering. Now, so as I say, and that sounds really like a strange situation, but that is the situation we've had for the last 50 years. Now, what happened was that in 1992, in some really seminal work that has not penetrated as much as it ought to have into the relativity community by the mathematicians Chris Duell and Kleinerman here at Princeton, the behavior at spatial infinity is more controlled than was generally believed. And you can tie these two groups together in a subtle way involving an antipodal map. So there is a symmetry of gravitational scattering that if you tie these super translations together, which involve an arbitrary function, by this antipodal map here. And that is an exact non-trivial symmetry of classical gravitational scattering. In other words, if you solve the problem where the two gravitational pulses come out at the same time, you can use the symmetry to get another solution of the scattering problem where they come out at different times. And this is infinitely many symmetries of gravitational scattering. So we could also talk about this in the language of the scattering matrix, which maps incoming states from past null infinity to outgoing states at future null infinity. And we learn that there's an operator B which implements this transformation, which commutes with the S matrix. So these symmetries, I want to say, are the true symmetries of GR. They're the non-physical, the non-redundant physical symmetries of GR. Now, whenever we have symmetries, we also have conservation laws. That's what Nether taught us. And when F is a constant, these super translations are ordinary translations, and we just get energy conservation. And so what do we get for the general F? Well, we learn that if we look at scry minus and we add up the flux of all the energy coming in through the north pole on scry minus, integrate it over the all advanced time, that will always exactly equal, in every gravitational scattering process, the outgoing energy at the north pole on scry plus. So there are infinitely many conserved quantities in general relativity. And I would note here that the energy in general relativity, to see that this works, you have to use the fact that the energy in general relativity at a given energy density at a given angle, as defined by Bondi, it's called the Bondi mass aspect, involves a term. It gets changed by a term which is linear in the metric fluctuation. Okay, so that's the story. The true symmetries of general relativity. There are infinitely many of them. They're an infinite dimensional group, and they're symmetries of gravitational scattering. Now let me turn to what seems like a completely different topic, but in fact it's the same topic, and I'm going to start to sketch out this triangle I alluded to in the second transparency. So now I'm going to talk about something that happened only 3 years after BMS in 1965. It's a famous paper by Steve Weinberg in which he had a number of results, and one of them was a so-called soft graviton theorem. And what Weinberg did was he said, take any scattering process, he was talking about quantum field theory, or quantum gravity, take any scattering process and that involves at least one graviton. Now let's take that, so we have n total in and out particles. Let's take that scattering process, compute the scattering amplitude, and then take the momentum of the incoming graviton and let it go to 0. The result of that is given by a universal formula, which is this funny function which involves the momentum of the graviton summed over the momenta of all the external particles and also the polarization tensor of the graviton, this funny function called the Weinberg soft factor times the same amplitude, but without the graviton. So this is a relationship between an S matrix element with n plus 1 particles and one with n particles. And it's an exact formula which applies to any consistent quantum theory of gravity. Okay. So now, this is related to BMS in an incredibly simple way. So we talked about this generator B, or the generator B of BMS transformations. It commutes with the S matrix. That's an operator statement. Let's take the matrix element of that operator statement, and that gives us some, when we write that out, that gives us some relationship between scattering amplitudes. And, okay, it's 4 or 5 pages, but all the conceptual things I've told you here, but it's 4 or 5 pages to translate from the momentum space language that Weinberg used to the asymptotic symmetry language that Bondi, Metzner, and Sachs used, but these are exactly the same. These are exactly the same statement. So I think it's kind of fascinating, if there's the historian of science is still in the audience, that these essentially equivalent discoveries, it's the same discoveries, it's the same formula, were made only 3 years apart. And I asked Weinberg about this, if he thought this was a coincidence that his formula had been derived in a different language across the ocean at basically the same time. And his response was, well, in those days, everybody was trying to do everything they could with symmetries and to make sense of them, and that was something that was across different communities. But they wrote their answers in such different forms that it took 50 years to recognize them as the same formula. Okay, now I'm going to go to what seems like a second apparent topic change, and that is gravitational memory. So gravitational memory, and this was discovered, but it's going to turn out to be the third corner of this triangle. So gravitational memory effect was discovered by Zeldovich and Polnarov in 1974. And the effect is this. So we had a beautiful talk about LIGO this morning. And in LIGO, the mirrors, when a gravity wave passes, the mirrors oscillate. And one measures, according to the quadrupole formula, the mirrors oscillate. So those would be these two purple lines, the oscillating mirrors. And you measure the AC oscillation, and that's what they hope to see at LIGO. Now, in fact, there's a DC effect. At the end of the day, after the wave has passed, the mirrors are not in the same position. In fact, they're attached to a pendulum, so they'll swing back. But at E Lisa, they're truly, or Lisa, they're inertial detectors, and they'll stay in the same position. So there's a DC effect of how far apart they are. And the formula for that was derived in 1974. It's been derived in many different ways by different people. And what one finds is that the final displacement of the detectors differs from the initial displacement by a term proportional to the change in the metric. And so you might be asking me, what's this about the change in the metric? I've got flat space here, I've got flat space here. The metric is going to be the same. What's this change in the metric here? Well, the change in the metric is, the statement is that not all flat metrics are the same, because they're equal up to diffeomorphisms or coordinate transformations, but not all coordinate transformations are trivial. Some of them are true symmetries, like the BMS transformations. So typically, what happens is when gravity or any other kind of wave passes through a region of space-time, the space-time is excited, and when it comes back after the excitation has passed, it returns to a different vacuum. It returns to a BMS inequivalent configuration, and that BMS transformation is exactly what is measured by the relative displacement in these inertial detectors. So this DC effect, it's smaller by a factor of 1 over r, where r is the difference to the source, than what we were hearing about this morning, but it's cumulative, and so that in some circumstances it adds up, it's not an oscillation. So there are proposals afloat to measure gravitational memory effect, and it's quite possible that it will be measured in coming decades. And the kinds of experiments you will do, and I think it would be very interesting to measure it, the kinds of experiments that you will do will be rather different. For example, it's well suited to things like the pulsar timing array, where it's something that you look at every couple of weeks, and if there's some offset, some DC offset in the timing of the pulsars that has happened any time in that 2 weeks, you'll be able to see it even if you only check it every few weeks. So here you see, to see this oscillating effect, you have to be watching as the waves are going through, but the DC effect, you can look at the distance and then you can come back a year later and measure it, and it's still there. Okay, so I alluded to what it had to do with BMS symmetry, but it's even more directly related to Weinberg's soft theorem. So here is a paper by Weinberg, a formula 2.7 from a paper by Weinberg. I'm sorry, there's a little bit blurry there, in 1965. And here is a paper 22 years later by Bruginski and Thorne. There are many ways of writing the gravitational memory effect, and you can see that these two formulas are almost exactly the same. So Weinberg uses little p to talk about the 4 momenta of elementary particles, and he uses q to talk about the momenta of the outgoing soft graviton. And here he's got a sum with the polarization, pp over p dot q. This is just to define the singularity. And here, Bruginski and Thorne, their p's are black holes and stars. I guess that's why they use capital P and Weinberg uses little p, because their things are bigger. And Bruginski and Thorne use k instead of q, but if you look at that, it's almost the same formula, but not quite, because Weinberg was working in momentum space, as field theorists are wont to do, and Thorne was working in position space. He wanted to know the change in the metric from early times to late times, which is the thing that is measured in the gravitational memory effect. And however, it's well known that if you have a pole in momentum space and you do a Fourier transform, you get a theta function. So you just have to fix up the notation, do a Fourier transform, and this Weinberg formula, 1965, is exactly the Bruginski-Thorne formula from 1987. And I think it's a beautiful thing that two people, not only from different kinds of communities, but one of them talking about little elementary particles and the other talking about black holes and stars, could derive exactly the same formula in nearly the same notation. And it's a reflection of the fact that this is a formula which has a very universal character. It's related to a fundamental symmetry of general relativity. It involves the deep infrared, and it appears in all kinds of different processes. It's a very robust formula. It's invariant under the exchange of elementary particles with black holes and stars. The other thing I like about this is it always bothered me a little bit, this discussion of soft gravitons, and also in the quantum field theory world, soft photons, soft gluons. How do we measure them? They have zero momentum. You can't really measure things that have zero momentum, but in fact, these people talked specifically about the measuring devices that would measure them. If you're in position space, you look at the positions of these detectors, and you see how it changes over a long period of time, and so that, I think, makes these soft gravitons much more physical objects. Okay, so this is summarized by a triangle of exact equivalence relations between three classes of physical phenomena, all of which have been studied for around a half a century. So just to summarize, we have the soft graviton theorem, which Weinberg discovered in 1965. Then we have BMS asymptotic symmetry. And whenever you have a symmetry, when you have quantum matrix elements, you can derive ward identities. And those infinite number of ward identities from these infinitely many symmetries are exactly Weinberg's soft graviton theorem. If BMS had never discovered their symmetry, we could have reverse engineered at this point, and we could have said, let's rewrite the soft graviton theorem in terms of it's some relationship between scattering from past to future null infinity. Let's rewrite it in that way and find out what the symmetry is. So the arrow goes two ways. Similarly, we can get between the memory effect and the soft theorem just by a Fourier transform. And I didn't go through all the details of this, but the existence of gravitational memory is due to the fact that, as BMS discovered, there are many inequivalent vacua in general relativity. It's not just flat. It's not just ordinary Minkowski space. You induce vacuum transitions whenever you breathe on the vacuum, and that's the gravitational memory effect. Now, I'd like to say, physics doesn't repeat itself, but it sometimes rhymes. And this is a quote that is neither due to Mark Twain nor Ed Witten, though they both said something very much like this. This triangle between soft theorems, asymptotic symmetries, and memory is something which is rhyming through many different areas of physics. So in that same paper, Weinberg also discussed the soft photon theorem. That's related to something called the electromagnetic memory effect, which a few papers have discussed. And it's also related to an infinite number of previously. Here we had to do the reverse engineering because the analysis that BMS did for gravity, even though it can be taken over basically word for word to electromagnetism, had never been done. And there are infinitely many non-trivial symmetries in ordinary QED. And there are also infinitely many conservation laws whose matrix elements are this soft photon theorem. Now, there are more soft theorems. There's a subleading soft graviton theorem, which has not to do with the pole, the leading term in the limit where the energy goes to zero, but the subleading term. And that turns out to be related by a ward identity to some newly conjectured symmetries of general relativity that people have been discussing for the last 10 or 15 years in general relativity and asymptotically flat spacetime. And there's an associated new kind of gravitational memory that has a handedness. And we described a gravitational spin memory effect that might also be measurable. In non-abelian gauge theories, there's a soft gluon theorem that's related to a kind of Kac-Moody symmetry and something called color memory, and on. So going back to the early work on, from the 60s in general relativity, we've gotten a whole new way of thinking about gauge and gravitational theories. Now, it also has important implications for the black hole information puzzle. As an aside, so first of all, the nohair theorems are theorems. They state that a black hole is characterized by, in Einstein gravity, by its mass and angular momentum. A stationary solution of the Einstein equation is characterized by its mass and angular momentum up to diffeomorphisms. Now, we wouldn't say that if you take a black hole and you boost it, that's the same physical object. It's got different energy and momentum. It's a different object. So we certainly don't want to say that all diffeomorphisms of the Schwarzschild solution are physically equivalent. But in fact, there's nothing special about the Lorentz group. In fact, there is no preferred Lorentz group in general relativity. We have to talk about all the BMS transformations. And so, yes, all solutions of the Einstein equations are equivalent up to diffeomorphisms, but there are infinitely many diffeomorphisms that act general coordinate transformations, I'm using the words interchangeably, that act on the Schwarzschild geometry, that give us new physically inequivalent configurations. So, for example, you can take the Schwarzschild solution, spherically symmetric Schwarzschild solution, you can act on it with a BMS transformation, and you can get a new stationary solution of the Einstein equation with non-zero angular momentum. So, in fact, there is an infinite amount of hair on black holes, an infinite amount of BMS hair that black holes carry. And one of the assumptions that went into the information puzzle, namely that, I should have said that, the information puzzle came up in Hawking's work, that if you have a black hole, you throw stuff in it, that information is lost after the black hole then evaporates and there's no sign of the information. So all of these 3 points invalidate the usual argument that information is destroyed. The second is that the conservation laws, these infinity of conservation laws that follow, that are encoded in BMS symmetry in Weinberg's soft graviton theorem, constrain the process of black hole evaporation. Of course, we're used to the idea that energy and momentum conservation constrain black hole evaporation. That is, the outgoing state of all the Hawking quanta if you add up all its energy, it must equal the incoming energy of the black hole. Similarly for the momentum. But that's not the only conservation law. There are infinitely many conservation laws, all on the same footing, which constrain the Hawking radiation, and so that will certainly affect the discussion. And finally, the vacuum itself is highly degenerate. We can do a BMS transformation on the vacuum and get a solution of the Einstein equation, which is the Riemann tensor vanishes everywhere, yet it carries non-zero angular momentum. So the vacuum in general relativity is infinitely degenerate, and there are infinitely many states, and therefore it can, in principle, can store information that came out of Hawking radiation. Okay, so the structure of symmetries in general relativity is certainly rich. It's confusing. We are probably still confused about it. We're certainly still confused about it. And it's amazing that a set of equations that was written down 100 years ago has caused us so much confusion, yet we've learned so much, and we keep learning more things. So I'll stop there.